Good evening and welcome to our presentation on Better Together, where we combine textual embeddings with node embeddings to perform the task of edge prediction or link prediction on citation networks. So what is this about? Given a snapshot of a network, you want to predict if two nodes are going to interact in the future with one another. In this context, it means that if you have two papers, which are nodes in the graph, is it possible for us to determine or predict if one paper is going to cite another paper, that is, have an edge between them in the future? In order to do this, and that's exactly what we wish to do in this project, there are text-based approaches and there are graph-based approaches, and we also wish to explore what would happen if we would combine textual embeddings with node embeddings. Would this increase performance or not? The significance of this is vast. This is one of the most popularly studied problems in the 21st century world today. It is helpful in social media to predict if a relationship can exist and if one person can be friends on Facebook with another person. It can also help predict future member collaborations in huge companies where there are more than 40,000 employees. We talk a little about our data now. We use the high energy physics citation network, which was taken from the SNAP group at Stanford, which is exactly where Professor Srijan did his postdoc as well. This dataset is pretty huge. It consists of 27,000 papers and has 350,000 citations, that is edges between them. And this is a temporal dataset, right? So there is time involved. So we have papers in 93, then papers in 94 and 95. So there is temporality involved in this dataset. The pre-processing wasn't too difficult, honestly, because the data was very clean to begin with. We just removed the excess text from the file because we only had to include the abstracts of the text, and then we would take all the abstracts and store them in one single file instead of having 27,000 different ones for different papers, right? And so we just include the abstract text because we're going to create textual embeddings from these abstracts. These are statistics of the data. You can see that the maximum in degree is 2,400, which means one paper is being cited that many times, and the maximum odd degree is more than 500. And yeah, it's a pretty big data set and a very useful one for our task. This is what the experimental setup looks like. So we did a classical 90% training and 10% testing split, and this consisted of an equal number of both positive as well as negative samples from the graph. For DeepWalk, which I'll get to in a bit what it is, for sentence transformers, and for our combined approach, where we combine both node and text embeddings, we use 30 training epochs with a slow learning rate of 10 power minus 4. And for Graph Sage, we used 100 training epochs with a 10 power minus 2 learning rate, and these values were determined completely empirically because they were the ones giving us the best results. For both the situations, we used the Adam optimizer and we used the binary cross entropy loss method. So yeah, once again, our task is to predict if nodes are going to interact in the future. That is, if one paper is going to cite another paper in the future. And this is what we did. We used that given method to create the embeddings. Right? It could be textual embeddings, or it could be node embeddings, or it could be a combination of the both. And then we predicted edges with these embeddings by training a multi-layer perceptron, a simple 2 to 3 layer perceptron model, which we trained using the binary cross entropy loss and the Adam optimizer. And then we carried out an evaluation of its performance using different metrics. And so now we talk a little about the approaches that we use. The first one is Graph Sage. Now, Graph Sage, you probably would have heard of it, is a very, very popular graph neural network that incorporates information not only of the node but also of the node's neighbors, right? So it encodes some relationship information as well to create embeddings. It's a really popular one of the state-of-the-art graph neural networks, and so we used this to create embeddings, and we achieved an accuracy of almost 80% and an ROC AUC score of 87.5. The next method we used was DeepWalk, which is another popular GNN. And this one is different from the previous one because it uses random walks. So if two papers are going to occur frequently together in the random walk, it means they're very similar, right? High chances they're going to cite one another. And so their embeddings are also going to be very similar. So that is why we chose this method. We trained our multi-layer perceptron on the embeddings that we got from DeepWalk, and we got an accuracy of 80%, ROC AUC score of 87.7. which was decent, sort of an improvement of the previous one. The third one we used was a simple NLP model, right? No graph information, no node embeddings, simply text information from the abstracts of the paper. Remember in the dataset pre-processing, I spoke about how we took the abstracts of all the papers. So we used those to create embeddings. We use a very specific model, which is a modified version of BERT. And we all know BERT is really amazing at creating embeddings. And we use this to create textual embeddings, and we trained our multi-layer perceptron on these embeddings. And we actually got really good results. we got an accuracy of 84.6 and an ROC of 92, which was more than the previous two methods. Definitely a great choice for our task. And then finally, we come to our combined approach. Talk a little about why we think this model will work, right? So when you generate node embeddings, you are definitely taking into consideration the structure of your graph. And so you are encoding neighbors' information into it, which is really useful when you're trying to cite papers, right? So you want to know the papers around you and whether they will frequently co-occur together or not. At the same time, it is also useful to have textual embeddings because the abstracts of the papers really contain what the paper is going to be about. It's going to have certain keywords, right? For instance, if a paper is about link prediction, it's going to have graphs and nodes and link predictions and graph neural networks and these sort of keywords, which is why text is also very, very important in helping us understand if there's an edge that will exist between two papers. Now, if you were to use both of them individually, you are definitely losing out on the other, and vice versa. So our idea was that if we were to concatenate these embeddings, or if we were to combine these embeddings, won't we get richer representations of our data? We'll get a much more significantly stronger representation of the information that we have, and then we can use this to train the neural network and more robustly predict edges between the nodes in the graph. And that was our philosophy and our whole fundamental idea behind coming up with this project. Now this is our idea, right? We have the abstracts and we create textual embeddings from the abstracts. We have our graph information where we create node embeddings, right, using DeepWalk, and then we combine both of them, which is as simple as doing torch.concatenate in PyTorch. So we combine both of these embeddings and then we train the network and then we predict. And our results were absolutely fantastic. Our ROC AUC score increased to 93.2, which was the highest, and an accuracy of 87.7, which was also the highest. So this is a model comparison, and as you can see, the bolded ones out are for the combined approach, and we achieved the highest metric scores for both of them. Conclusion is that the combined approach definitely seems to be a great way to go about it, but the existing graph and NLP methods are also fairly effective for edge prediction, and a lot of research can be done. This takes me to future work where we can try GraphSage or other GCNs on node and text embeddings concatenated with one another, and this would take place before the embeddings are learned. So this is something that we can definitely explore in the future. Thank you very much, and I hope you enjoyed my presentation.